Okay, so measuring the variability in the data adds a new dimension to the central tendency. And these are 5 important measures of variability or dispersion. The variance, standard deviation, and standard error are closely connected and are based on the square distance of each observation from the mean, which I'll get back to what that means. These are commonly used with interval or ratio types of variables. The range and interquartile range are often used when data are highly skewed and for variables that are not of the interval or ratio type. Okay, the range is perhaps the most basic measure of dispersion. It's simply the difference between the greatest and lowest observation. So returning to the data set from before, we see that the range in this case is 72 minus 1, which is 71. So when is this useful? Well, say we have a questionnaire with 10 alternatives ranging from strongly disagree to strongly agree. And we give them the values 1 to 10, so that strongly disagree is 1 and strongly agree is 10, and then we have all the other values in between. This would be an ordinal variable that is not on an interval scale, right? We can't say that strongly agree is 10 times as much as strongly disagree. So we use the median as our measure of central tendency. If the median is 5, it's very interesting to know whether the range was 9, which means that all values were used, right? So somebody said 1 and somebody said 10. And actually it doesn't mean all values because nobody had to have to say 9 or 2, but at least one person said 1, at least one person said 10. And it would be very interesting to know if the range was 9 or if it was, for example, 0, which would be the other extreme, which means that everybody said the same thing. Everybody said 5. Very often the range is given as 2 numbers, like 1 to 72. So we can have that the range is 71, or we can say that the range is from 1 to 72. Another example of when the range is useful is if we want to describe limitations. For example, you could say that the youngest player who took part in the World Cup in some sport was 17 and the oldest was 42. That's a range right there. And of course, it's highly sensitive to outliers. The variance of a sample is, like I said, the mean squared distance from the mean value of all observations. So all statistical software can easily calculate the variance, so you will probably never really have to use the formula or even understand it conceptually unless you want to. Still, I will spend some time sometimes going through the mathematics behind the variance. The standard deviation, of course, is a much more commonly used metric, and we'll get there shortly, but the standard deviation is very closely connected to the variance. So that's why we talk about the variance first. Okay, so now if you want to go grab a cup of coffee with this video on in the background because you don't care about the mathematics, this is a good time to do that. Okay, so in the formula on this page, the mean of all observations is the x with a bar. So the x with a bar means x1 plus x2 plus x3 and so on divided by n. The sigma, the Greek letter, means that we sum over all values of I. In other words, we first calculate the mean, then we take x1 minus the mean and square it, x2 minus the mean and square it, and so on, and we add all of those squared differences together. And then finally we divide, and we don't actually divide by n, but by n minus 1 to get the mean. And the n minus 1 is there for a very subtle mathematical reason, but we will not get into that. So when I say the mean square distance, it's actually not exactly the mean square distance, but it's this is slightly better. Uh, the variance is a very important measure, but like I said, we mostly work with the standard deviation, and this has to do with something that's very obvious here. 389 just seems like a very excessive measure of the variability in the sample at the top of the page. So it ranges from 1 to 72, but the variability is almost 400. It doesn't make much sense. So that's where the standard deviation is handy. So the standard deviation of a sample is the square root of the variance. And this ensures that the scale of the standard deviation is the same as the scale of the variable. So it's not 400 anymore, it's 19.7. For example, or another example is if we measure the height of people, then the variance is going to be measured in square meters, but the standard deviation is going to be measured in meters. So, that's we can see that measuring the variability of the heights between people is it's not very useful to use square meters. Okay, there are two ways of understanding the variance, and they are there's a subtle difference, but the difference is there. The first one we have talked about this far, and that's variance and standard deviation as properties of a sample, or in other words, we talk about the sample variance or the sample standard deviation. And that means that we may calculate the variance in a sample and then take the square root to get the standard deviation. So then we use the formula that we talked about. The second concept or the second understanding of the variance and standard deviation is that they are a property of an underlying distribution. For example, if a variable is normally distributed, like the height of Norwegian 19-year-old men, then this normal distribution has a fixed standard deviation. And in the case of the 19-year-olds, it's 7 centimeters. So the mean is about 180 centimeters and the standard deviation is 7. And this is true regardless of any sample we may draw. So in our sample, the standard deviation may be different from 7 centimeters, but in the underlying population, the standard deviation is 7 centimeters always. And we may, if we have a very large random sample, then the sample standard deviation is going to be very close to the true underlying standard deviation. Okay, so the standard error is the standard deviation of the mean in the sample, and this is different from the standard deviation in the sample. The standard error lets us know how sure we can be that the mean in the sample is close to the true mean in the population. And we get there by dividing by the square root of n. So if we have 100 individuals in our sample, we divide by 10. If we have 10,000 individuals in the sample, we divide the standard deviation, the sample standard deviation by 100. If we only have 4 individuals in our sample, we divide the sample standard deviation by the square root of 4, which is 2. So that means in order to double the precision, we have to increase the sample size by 4-fold. Okay, so for large samples, the standard error is going to be small, right? We can see that from this formula. If we increase n and we don't do anything with the standard deviation of x, then the standard error is going to be to get smaller. So that's what we just talked about. And I know the difference between standard deviation and standard error is often confusing, but let me try to motivate with an example. And I hope this is an okay example. Let's consider a department that teaches 26 courses. The courses vary in size. There are large introductory courses and very specialized PhD courses with just a handful of students, right? So the size of these shapes sort of represent the size of the courses. We have one very large course and some very small courses and everything in between. Now, let's just, to make this simple, say it's an all-male school and we are interested in measuring the heights of the students attending the courses. So regarding heights, the courses could be seen as random samples of the total student population, right? Because we have no reason to think that, for example, tall students are more likely to take a statistics class than short students. So if I know, if the only thing I know about you is which class you're attending, I know nothing about your height, right? Now say these are the mean heights in each course. And if you were asked to give an estimate of the mean height among all students in the school, but you were only allowed to measure the heights in one course, would you pick a course with few students or with many students? So think about that for 5 seconds. Now, if you answered many students, you are correct. Note that the difference between the classes is very large for the small classes. It ranges from 164 to 194 for the 7 smallest classes, right? So a difference between the mean heights, because this is the mean we're talking about, right? So the difference between mean heights of 30 centimeters from the shortest to the tallest class. And maybe these guys who were 194 at the top right corner, maybe there were just 2 people in this class, right? Because they're small. It's small, there were 2 people and they just happened to be tall, both of them. And maybe the one with 164, maybe that's just one student. And he happened to be short. So still, we calculate the mean, we get huge differences between the classes, right? So if we have few individuals in a class, then the mean is going to be highly affected by the height of each individual. In the largest classes, there may be hundreds of students. So if there are 1 or 2 students that are very short or very tall, it's not going to affect the mean all that much. Therefore, the mean height in the large classes is going to be close to the population mean of about 180 centimeters. So this is what the standard error measures, right? How much do we expect the mean to vary between groups of the same size? So we see here in the 4 largest classes, the mean varies by just 2 centimeters or 3 centimeters from 178 to 181. And that's why the standard error is going to be small when classes are large and large when classes are small. It's important to emphasize that the standard deviation in the large class or the largest classes is going to be about 7 centimeters. So the sample standard deviation is going to be about centimeters if the standard deviation in the full student population is 7 centimeters, which we just talked about. So the standard deviation has nothing to do with sample size. The sample standard deviation in the small classes may be far from 7, but the underlying standard deviation is going to be 7. And the sample standard deviation in the large classes is also going to be close to 7. Okay, so one slide about the interquartile range. So the interquartile range is just the difference between the first and third quartiles. It can be presented either as a single number. In our example, we have 10 minus 2 equals 8, or we could say from 2 to 10. That would sort of add one extra number to our measure. The interquartile range is useful in situations where we use the median as a measure of central tendency. It's robust to outliers, whereas the standard deviation is not. It may also be used for ordinal variables that are not on an interval scale. So if we return to the example with the questionnaire that I mentioned earlier, we remember that possible values were 1, 2, 3, and so on, all the way through 10, and also that the median was 5. Now, an interquartile range of 2, which is quite narrow, would suggest that the data was located closely around 5, right? So it would mean that half the data was within 2 units. So maybe from 5 to 6, 5 to 7, or 4 to 6, or something like that. Whereas a large interquartile range, if we say 7, for example, it would suggest that people's opinions varied more. So it would mean that half the people would answer between, say, 2 and 9, right? And this scale only goes from 1 to 10. So that's a quite different situation. In the example with age in the World Cup, let's say that the median age among all players was 26, and the interquartile range was from 23 to 32, and then we had the maximum of 42 and the minimum of 17. And this would mean that the age distribution was a bit skewed, right? So a quarter of the players would be between 17 and 23. A quarter would be older than 32. That means between 32 and 42. So that's a 6-year span, right? Whereas in the youngest quarter, that's a 10-year span, I mean, whereas in the youngest quarter, there was only a 6-year span. And then we have another, then we have a 3-year span from 23 to 26, which contains another quarter of the population, and then a 6-year span from 26 to 32, which contains 1 quarter. So that's, yeah, if you can make a mental image of that, then you see that it's the distribution is slightly skewed, but it's nothing dramatic. Okay, so returning to our original example, this is one version of a box plot of the data. So a box plot is just a way to visually present the data using some of the measures we have discussed so far. The squares at the bottom are usually not included, but I like to put them there, and they just denote the observations. It's sort of a histogram. Then we have the minimum and the maximum. We have Q1 and Q3, the ends or each side of the box. Then we have the median, which is the thick line in the middle of the box. And then I included the mean, which is actually normally not included in a box plot, but I just wanted to show what it looked like when we compare it to or with the median and the data. So as we can see and remember, the mean is higher than all but 4 of the 17 observations. But the median is right in the middle, and it doesn't care that some observations are really high. And we can also see here that the mean is in an area where there's really no data. So our measure of central tendency would then be a number that's far from any number we've actually observed in the data, which is a bit dubious. The mode is also a bit dubious in this case. It's 2, so we can see the stack of 3. So unless the mode is, unless there are lots of individuals that have the mode value, then it's very often not particularly useful. And I would say in this situation, it's probably not a good measure of central tendency. Okay, so that's all for now in this lecture on basic concepts in statistics. The next lecture will be on statistical inference, including tests and confidence intervals. So see you then.